Thank you.
Let's start.
So today we will be learning introduction to deep learning in computer vision. Deep learning is a powerful part of machine learning. It uses deep neural networks, complex multi-layered systems to learn intricate patterns. This capability is why it's so transformative. During breakthroughs in areas like image and speech recognition and even natural language understanding. Computer vision empowers machines to see and interpret visual data. It's the technology behind self-driving cars, medical image analysis, and countless other applications where visual understanding is crucial. Before start, let's watch this short video.
Deep learning has revolutionized computer vision, and it is the core technology behind capabilities like self-driving cars. This series will quickly get you up to speed in deep learning. We'll use TensorFlow and the TensorFlow implementation of Keras. TensorFlow is the most popular tool for deep learning, and Keras is a popular API or interface for specifying deep learning models. Keras started as a standalone library for specifying deep learning models, which could then be run in TensorFlow as well as in some other deep learning computation engines. The standalone Keras library still exists, but TensorFlow has become the dominant engine for deep learning, so the creator of Keras implemented a version of Keras that is built into TensorFlow. This allows you to specify models with the elegance of Keras while taking greater advantage of some powerful TensorFlow features. We'll cover topics in a different order than most academic sources. Other courses start with technical or theoretical details and eventually build up to something that you can apply. In this series, you'll start running powerful models soon to get hands-on experience using deep learning. Then we'll come back to the technical details you need for fine-tuning your models and addressing novel applications. Your machine learning experience so far has probably focused on tabular data like you'd work with in pandas. We'll be doing deep learning with images, so we'll start with an overview of how images are stored for machine learning. Here I have the image of a handwritten digit, the number 2. It's composed of pixels. Some pixels are completely black, some are completely white, and some are varying shades of gray. The pixels are arranged in rows and columns, so it's natural to store them in a matrix. The matrix would look roughly like this. Each value represents the darkness of a pixel in the image. The number in the upper left of the matrix indicates how dark the upper left pixel in the image is. Go down a row in the matrix and we get how dark the pixel 1 row down in the image is. I made this a small matrix to fit on your screen, so the real matrix would be larger than what you see here, but it would have exactly the same format. Color images have an extra dimension. For each pixel, we store how red that pixel is, how green it is, and how blue it is. It's like a stack of 3 matrices. Tensor is the word for something that is like a matrix, but which can have any number of dimensions. So we'll call them tensors moving forward. For now, let's go back to the grayscale image, which has a 2D tensor representing the darkness of each pixel. Today's deep learning models apply something called convolutions to this type of tensor. A convolution is a small tensor that can be multiplied over little sections of the main image. Here is an example of a convolution. Convolutions are also called filters because depending on the values in that convolutional array, it can pick out specific patterns from the image. I propose that the convolution you see here is a horizontal line detector. If you multiply it on a part of the image that has a horizontal line, you get a large value. If you multiply it on a part of the image without a horizontal line, it gives a value close to 0. Let's see a simple example. Here we have a part of the image where all of the pixels are the same intensity. We do array-style multiplication, multiplying the upper left values in each tensor, and then the upper right values in each tensor, and so on. Then we sum them to get the results. So we get 1.5 times 200 plus 1.5 times 200 minus 1.5 times 200 minus 1.5 times 200. For this particular convolution and this set of pixel values, we get a result of 0. Doing the same thing where we have a white area, like this, we get 1.5 times 0 in each cell, so we get 0 again. Let's use the same convolution where we have dark pixels above some light pixels. In other words, over a horizontal line. We do the multiplication and the addition. We get 1.5 times 200 plus 1.5 times 200 plus 0 plus 0. This time, we really did get a big number. So this convolution really does work at detecting horizontal lines. This particular convolution was 2 rows by 2 columns, and we could use other size convolutions like 3 by 3. The numeric values in the convolution determine what pattern it detects. We'll come back to show you how you get those numbers. But we'll start with a short exercise to see convolutions in action. Once you've done the exercise and you have a good grasp of a single convolution, you'll learn how combining many convolutions can create powerful models. Read on below to get started.
So let's get further. The Kaggle Deep Learning course, it's a fantastic resource for learning and applying deep learning techniques. This course provides a foundational understanding of deep learning. It teaches you how to create fully connected neural networks using Keras and TensorFlow, applies them to classic machine learning problems, and improves their performance through various optimization techniques. This course begins with the linear unit, which is a basic building block of neural network. You'll learn how input, weights, and biases interact and how to create linear models using Keras. You'll learn how to use Keras sequential to build neural networks models, defining dense layers and input shapes. The course emphasizes practical application, allowing you to create models for various tasks. A significant portion of the course focuses on training and optimization. You'll learn how to train neural networks using stochastic gradient descent and improve their performance with techniques like dropout and batch normalization. These techniques are crucial for building effective neural networks. The course emphasizes practical application, allowing you to apply neural networks to real-world data sets and classic machine learning problems through hands-on exercises. Let's recap Kaggle's computer vision course, where we learned to teach computers to see through image classification. This is important because computer vision is rapidly transforming industries from autonomous vehicles to medical diagnostics. This course focused on practical computer vision skills. We learned to build powerful image classifiers, design computer networks, and enhance our models with transfer, learning, and data augmentation. These skills are essential for anyone wanting to work with image data in real-world application. Convolutional neural networks, we say ConvNet or CNN instead, are the core of modern computer vision. This is important because the ability to automatically learn special hierarchies of features makes them vastly superior to traditional methods for image analysis. We delved into roles of convolutional base and dense head. Understanding this structure is crucial because it allows us to build networks that can effectively process and interpret complex visual information. A key component of the course is transfer learning. This is important because it enables us to achieve high accuracy with limited data, saving time and resources. In real world scenarios, pre trained models are often the starting point for building sophisticated vision systems. Data augmentation helps us to create more robust models. This is crucial because it allows us to train models that perform well on unseen data, which is essential for deploying reliable computer vision systems. In this course, you will get experience in building and training models using Keras. This is important because Keras simplifies the development process, allowing us to quickly iterate the experience with different model architectures and training strategies. Convolutional neural networks are essential. Transfer learning is powerful. Data augmentation is crucial. Keras makes it all accessible. These skills are highly relevant in today's AI-driven world, where computer vision is used in a wide range of applications. So our homework will be deep learning at Kaggle, and another homework will be Kaggle computer vision. Thank you. I also want to share that I, a couple of years ago, tested self-driving cars. It was Chinese software for self-driving cars. It was very interesting experience. Also, Google made self-driving cars, Waymo. They drive in San Francisco. You can Google some share experience by driving these self-driving cars and share it on YouTube and other social media. So it's a very interesting experience. Also, I was on Meetup in Poland where people from Waymo project were sharing how they're working, how they're building their self-driving cars. It was very interesting.
If it's possible, you can share these projects with attendees. It's really exciting.
Yeah, I can send links in our chat later.
Oh,
Also,
Discord channel. Yes, Discord channel works
yeah.
perfect for attendees.
Also, if you want to learn more about self-driving cars, there are very interesting courses on Coursera, also on Udemy. So you can learn more about this. Thank you.